One of the things you need to succeed in this IB Physics course is a few math skills. I tried to list them quite exhaustively here. Number 1 through 4 I will cover in this video, 5 through 8 in the next video, and number 9, well, I'll do it later on in the course. So let's start with the first one. Let's go through this crash course in math for you to do well in IB Physics. First, multiplying numbers. Well, you know how to multiply numbers, but in physics it can get a bit tricky because you're dealing with numbers written in scientific notation. You have to be careful that you put them in the right units before multiplying them, and to give your answer with the right amount of significant figures. So let's look at a problem where we're going to apply this combination of skills. Here's the Earth and the Moon. The goal of the problem is to find the force of attraction between the two, the gravitational pull between the Earth and the Moon. So what equation do we need for this? Well, what about Newton's universal law of the gravitational force that I showed in the previous video? So it seems like we need the gravitational constant, the mass of the Earth, the mass of the Moon, and the distance between Earth and Moon. Let's go look it up on Google and write them down on our diagram. And here's the data. Thank you very much, Google. We have the mass of the Moon here, we have the mass of the Earth, we have the distance between the Earth and the Moon, and we have the universal gravity constant. So now let's plug them inside Newton's equation and see what we get. So here's the expression you obtain, and I put a mistake in there on purpose to see if you can spot it. So pause the video and try this out. The mistake is here. 384,400 should be converted into meters. It's in kilometers here, and we want something in meters so that everything is in SI units, and I'm sure to obtain newtons as units in the end. So here I have to rewrite this as 384,400,000 meters, and this value is squared. So let's make this more neat by writing everything in scientific notation. And here it is. Okay, at this stage you have two choices. You can plug this directly in your calculator. This is what I usually do. But some students find it useful to separate the numbers and the powers of 10 such that they add an extra step and make it extra sure that they get the answer right. And this is what you obtain by separating the figures and the powers of 10, and pay particular attention to the green number here, where the square, of course, applies both to the figure, 3.844 squared, and to the power of 10. 10 to the 8 squared gives me 10 to the 16. Okay, when I plug these numbers in my calculators, I obtain this figure on my screen, and now are you able to make this calculation? Pause the video and try it on your own. You obtain minus 11 plus 22 is 11, plus 24 is 35, minus 16 is 19. So here I obtain 10 to the 19, and little drum roll, I'm going to write the final answer here, 19.80 times 10 to the 19. Ta-da! Well, no, you should react with a uh-oh, because there are 3 mistakes in there. Can you spot them all? I assume that you paused the video and gave it a shot. Well, the first obvious mistake is the units. This is a big no-no. You clearly lose points whenever you forget units. The second mistake is the amount of significant figures. Here I gave my final answer with 4 significant figures, and I have to round it to 19.8 because I have some data which is with 3 significant figures, like the mass of the Earth and the gravitational constant that I found from the data booklet. And the third and final mistake, well, it's not really a mistake, it's just that when you have very big numbers, it's good practice to write them in scientific notation. So here we have 1.98 times 10 times 10 to the 19. So 1.98 times 10 to the 20 newtons, and that's the final answer with the correct amount of significant figures, with the correct power of 10, and with the correct units. Students usually have some trouble with writing the correct amount of significant figures. For example, when they obtain something like 0.02050, they think, gee, which are the zeros that count and which don't count? Well, the easy rule is that all the zeros before the first non-zero digit don't count. So here we have 4 significant figures. And here's another tip. Write your number in scientific notation. Here, 2.050 times 10 to the minus 2. In scientific notation, all the figures count. So here you easily see that you have 4 significant figures. Please also beware of something else. When a physicist says this thing has a mass of 4,300 kilograms, well, he is actually being precise to the 100 of kilograms. This is implicitly understood. If he really wanted to say 4,300 kilograms, and I'm precise to the kilogram, he would say 4,300 point kilograms. He would write it this way. So this number has 2 significant figures, and this one has 4 significant figures. Phew, I took 5 minutes to explain how to multiply numbers together, and I'm a pretty fast talker. See, it's not that easy in physics to multiply numbers together. Okay, let's go to the next one, and I promise that it's going to be easier. We want to learn how to solve for a variable, and let's look at a practical problem to illustrate how we use this math skill. I have a ball rolling down a plane, and the goal is to predict the time that it's going to take to reach the ground, knowing that the length of the plane is 1.5 meters and its angle of inclination is 20 degrees. So how do I solve this problem? Well, I know that the ball is experiencing uniform acceleration, so I can use an equation that relates these variables together when we are under these conditions. And here is the equation. And here's the equation that applies to uniform acceleration, and you'll learn in another video why this is the case. You know this term already, actually. Distance is equal to speed times time. And when you have a constant acceleration, you have to add this term, 1/2 of at squared, where a is the acceleration. Okay, so let's use this equation to solve our problem. First, we realize that we're dropping our ball from rest, so the initial velocity here is 0. So I can just get rid of that term. I'm left with s is equal to 1/2 of at squared. And this is how we're going to learn how to solve for a variable. What does it mean? It means that I want t in terms of the other variable so that I can find time. So what do I do first? I can multiply by 2 and divide by a on both sides, and I obtain t squared is equal to 2s divided by a. And finally, I can take the square root on both sides, and I obtain t is equal to root of 2s divided by a. Now I'm almost ready to plug in numbers and solve my equation, but the problem is that I don't know the acceleration, and that you'll also learn later. But when an object is rolling down a plane, the acceleration is equal to g times the sine of the angle of inclination. So here I have t in terms of distance and acceleration. Well, I also have to put acceleration in terms of things we know, meaning gravity and the angle of inclination. So I obtain t is equal to square root of 2s divided by g sine theta, where theta is the angle of inclination. Now I just have to plug in the numbers. So square root of 2 times 1.5 meters divided by 9.8 meters per second squared, this is in your data booklet, times sine of 20 degrees. Everything is in SI units, and I can now write my final answer using my calculator. And I obtain 0.95 seconds. Of course, I didn't forget to put my units, and I express my answer with 2 significant figures because I have 2 significant figures for the plane length and the angle of inclination. Okay, let's move on to the third skill I want you to develop in this video, which is to perform dimensional analysis. And that's probably the most important one in this video. This is the one that will prevent you from making mistakes on exams and losing points when you're solving equations. Let me explain. We just saw the equation for uniform acceleration when the object starts at rest. And then we solved for t. And we found that this equation is equivalent to t is equal to root of 2s divided by a. And now there's a way to check if I made a mistake going from this step to this step, and this is called dimensional analysis. I'm going to analyze if the units on the left side make sense with the units on the right side. On the left side, I have seconds. Do I have seconds on the right side as well? Well, let's check. I have the square root of something in the numerator that's a distance, so it's in meters, and something in the denominator, which is in meters per second squared. It's an acceleration. And how do I know this? Because I know that an acceleration is a change of velocity divided by the time that it took to change this velocity. So I have something in meters per second divided by seconds, meters per second squared. Okay, so what do I get? Well, the meters cancel out. I have per second squared on the denominator, so that becomes a second squared on the numerator. And I have the root of something in seconds squared, so indeed this is something in seconds. I have the same units on the left and on the right hand side, meaning that my equation at least makes sense as far as units are concerned. Let me give you another problem so you can perfect this skill. Let's look again at the expression of the gravitational force between two masses which are separated by a distance r. We saw that g, the gravitational constant, was equal to 6.67 times 10 to the minus 11, and that this amount was coherent with SI units. But what are the units of this number? Well, we just have to put g in terms of the other variables. So I'm going to multiply by r squared and divide by m1, m2 on both sides, and I obtain this expression. And now I'm going to write the answer, so I really encourage you to pause the video and try to find the units of g on your own. The units of g are a unit of force in newtons times a unit of distance squared, meter squared, divided by kilograms and kilograms again, so divided by kilograms squared. Is that correct? Let's check in the data booklet. And sure enough, referring to the first page of your data booklet, we find the value of g, which is indeed 6.67 times 10 to the minus 11 newtons meter squared per kilogram squared. So that's dimensional analysis, and rereading my page, I realize that there may be a source of confusion here. This s expresses the variable for distance, and this s is the unit for time, seconds. So here we have distance, and here this s expresses seconds. Just wanted to make sure that you didn't get confused on this one. Let's now move on to the next item, performing basic operations on vectors. Why do we do operations on vectors and not just numbers? Because in physics, well, we have variables like forces, which we represent this way, which are vectors because not only they have a magnitude, but they also have a direction. This is what this little hat means. This is what makes f a vector here, because it has both a direction and a magnitude. And for example, to express a force, we can say 1,000 newtons down, and this expresses both the magnitude and the direction. So now let's look at a problem where we can see how this works. In this example, I have a car moving on the highway, and it's being subject to these three different forces. Now, there is a mistake in this free body diagram, and first question is, what is this mistake? What is missing here? This drawing doesn't make sense at all. I'll encourage you to pause the video and try to think about it on your own. And here it is, the reaction from the ground, which your textbook might call the normal force. Why do we have this reaction? Well, if your free body diagram only had these three forces, it would mean that your car is being accelerated downward, and I don't see it personally going through the ground. Okay, the ground is reacting to the weight of the car, and actually the reaction and the weight should be equal in magnitude and opposite in direction, which correctly expresses the fact that your car is neither flying upwards nor going through the ground downwards. Okay, so what's the question here? The question is, what is the net effect of all these forces together? What is the net force? And to find that, we have to sum all these vectors together. So how do we perform vector sum on these four vectors? I'm trying to find something that's called f, vector f, which is equal to the sum of the weight, vector weight, the vector for the reaction force, the vector for the thrust force, and the vector for the drag force. So how do I add all these together? Well, to simplify the problem, first you can separate what's happening in the vertical direction and in the horizontal direction. You can consider these independently. And you see that in the vertical direction, well, the weight and the reaction compensate each other. They balance each other out such that the vector w plus the vector r is 0. It's nothing. Okay, so the thing that's interesting is happening in the horizontal direction. Here we have a force towards the right, which is 1,500 newtons, and a force towards the left of 200 newtons. And the method to sum two vectors goes as follows. First, you take the thrust vector. I made it a lot larger to illustrate the thing better. So I have my t vector, which has a magnitude of 1,500 newtons, represented by the length of the vector here. Then if I want to sum my t and my d vector, well, I just put them end to end. I start at the end of the t vector, and from there, I draw my d vector that goes backward here. So here I have d of magnitude 200 newtons. And the resulting sum of t and d is you go from the beginning of t all the way until the end of the sum. Okay, so you go until the end of the d vector here. And here you obtain the net effect of t and d, which is a vector that goes towards the right with a magnitude of 1,300 newtons. So my final answer is 1,300 newtons right. Okay, I express both the magnitude here and the direction here. And you could also define a convention saying that this direction is the positive direction. Okay, we often do this. We often define the direction of motion as the positive direction. So here in the end, you could just say plus 1,300 newtons, and you're done with this problem. I imagine that you must be a bit tired by now, and frankly, I understand you. I mean, you've been going through 15 minutes of rather dense lecturing of math and physics, but hang in there. This is the last problem that I'll be showing in this video. Why did I add this problem? Well, you've been summing vectors in one dimension, and that's rather easy. The IB also requires you to develop the skill of summing vectors in 2 dimensions, and here I have a problem in 2D, where I have this mass, which is being held by these 2 ropes in tension. Okay, so the question is, what are the forces acting on this mass? What is the magnitude and the direction of each force acting on this mass? To answer this question, you need to draw a free body diagram of this mass. You know that it feels its own weight, in this case 10 kilos times gravity, which I will round to 10 Newton per kilos, so I have a weight of around 100 newtons. That's the easy part. And then that's the less easy part. I have 2 tension forces, one in this diagonal direction and another one in this other diagonal direction. And my goal now is to find the magnitude of these 2 tension forces. Well, let's use vector sum, because I know that this object is at rest. It's not being accelerated in any direction. So the sum of all these forces has to have a 0 net effect. So let's do another drawing in this space, which illustrates what I just said, the fact that when you add the weight, the green tension and the blue tension, when you add all these vectors together, you obtain nothing. And look how this happens. Here I have my weight, which has a magnitude 100. Then I add the green t. Then I add the blue t. So I put them all end to end to add them up. And indeed, the yellow arrow plus the green arrow plus the blue arrow makes me return to the same point of origin. So this drawing expresses well the fact that my object is at rest, and the combination of the 3 forces results in a 0 net force. Okay, so the goal now is to express this length t here. This is my unknown. I want to know how much tension force I have in each of these ropes here. And to do this, well, I realized that each of these t vectors is contributing for half of this vertical displacement from bottom to top, right? So here I should have a length of 50, a magnitude of 50 for the vertical projection of this vector, of this green vector on the yellow one. Okay, and how do I put this in relation with t? Well, this is the length t, and I know that I have an angle of 45 degrees here. So the vertical projection of t here, that I will note in orange, this vertical projection, which is equal to 50 in magnitude, it's also equal to t times the sine of 45 degrees. Okay, so t times the sine of 45 degrees is equal to 50. Dividing by sine of 45 on both sides, I get that t is equal to 50 divided by 1 over root 2, which is the sine of 45 degrees. And I obtained that t is equal to 50 times root 2, which is approximately equal to 71 newtons. Okay, we're ready to conclude. We have this weight, which is equal to 100 newton in the downward direction. We have this green tension force, which is 71 newtons at a direction of 45 degrees compared to the horizontal. And finally, we have this other tension force, which is also 71 newtons, and it forms also an angle of 45 degrees compared to the horizontal axis going to the left. That's it for today. We went over these 4 math skills that you'll need for IB Physics, and in the next video I will go through skills 5 through 8. Thanks for watching.